Hi, good to see you all through this social media platform in a new topic, Pulse with Modulation. Myself Aishwarya. I am working as an assistant professor in the Department of Biomedical Engineering in Emmanuel SHG College of Engineering. Okay, let's begin the section. So today we are going to see about a new topic, PWM. PWM is nothing but pulse with modulation. Pulse width modulation. Actually, PWM is a technique used to control the amount of power delivered to a load by switching a power supply on and off at a high frequency. The power pulse width modulation generates a square wave signal with a constant frequency and a variable duty cycle. The average value of a voltage fed to the load is controlled by switching the supply between 0 and 100 degree at a rate faster than it takes the load to change significantly. So pulse width modulation is a technique actually controlling for switching the supply on and off. Okay, so instead of changing the voltage level, the PWM, that is the pulse width modulation, changes the on time, that is the pulse width, while keeping the voltage constant. So it keeps the constantly voltage and it changes into the on time. So actually the definition of pulse width modulation is defined as PWM, that is pulse width modulation, is the process of varying the duty cycle of a square wave to control the power supplied to electronic devices. Okay, so it is nothing but the process of varying the duty cycle, that is on to off or off to on, of a square wave to control the power supplied to electronic devices. Okay. So why we should go for pulse width modulation? Because it is efficient power control, it has low heat generation, it has high speed switching, it has better motor control and easy implementation using microcontrollers. Okay, due to these reasons we are using pulse width modulation in the embedded systems. Okay. So what are the parameters here? That is the pulse. What are the pulse used for? Any voltage passed into the microcontroller is the pulse, and on time, period of time controller which receives some voltages is used is called as on time. So again, off time. What is off time actually? The period of time microcontroller which does not receive any voltage. So off time means it does not receive any voltage. On time means it receives some voltages. So width length, what is actually the width length? The length of on time and the off time is called as the width. Again, PWM, which is used increase or decrease, that is which modulate or change the width of the pulse. So which changes the width of the pulse is used for pulse width modulation. Again, duty cycle, that is time on or time on plus time off in percentage, which is given as duty cycles. T on means on time, T off means off time. Okay, this is the parameters which is used in the pulse width modulation, that is pulse, on time, off time, width, PWM, then duty cycle. In the duty cycle only we have on time and off time. Okay. Again, the pulse width pulse width modulation wave, how they are used. For example, if a perfect square wave with equal high time and low time has a duty cycle of 50%, okay, it has only the duty cycle of 50%, then here is the diagram showing different duty cycle in a general way. Okay, see, the first graph is what? See, the first graph you have 50 duty cycle, the second one you have 75 duty cycle, and the third one you have 25 duty cycle. So for 25 you have little bit, and then 50 you have more than that, and then the 75 you have bigger than that, right? So this is the duty cycle differences which was mentioned in the PWM. Okay. So why the working principle of PWM consists of on time and off time, as I have mentioned earlier. So on time is considered as T on and off time is considered as T off. So the total period will becomes T is equal to T on plus T off. Okay, so the frequency will always be 1 by T. The frequency will be always equal to 1 by T. Okay, so this is the frequency. The frequency will always become 1 by T. Okay. So what are the registers actually using here? The registers are prescalers, auto reload registers, that is ARR, or counter or period. Then it is the next one is duty cycle or pulse. Okay, so these three are the registers: prescaler, auto reload registers ARR, or counter or period. Okay. So next one is the duty cycle or pulse. So what is this duty cycle actually called as? The duty cycle is the percentage of on time. Okay, so duty cycle is the percentage of on time that is mentioned as, see, duty cycle is actually the percentage which is equal to T on divided by T in the whole into 100. Okay, this is actually the duty cycle. So duty cycle is nothing but the percentage is equal to T on by T into 100. So this is called as the duty cycle. Okay, so duty cycle is the percentage of on time, so that duty cycle percentage is given as T on by T into 100. Okay, so the prescaler is actually, it is an electronic counting circuit used to reduce high frequency electrical signals to low frequency by integer divisions. Okay, it is electronic counting circuit used to reduce the high frequency electrical signals to lower frequency by integer divisions. So the prescaler value is set in the prescaler register of the time. The prescaler value is set in the prescaler register of the timer. So the prescaler can be set to any value from 0 to 65 535, but the maximum value will depends upon the bit size. What are the bit we are giving, that will depends on that. So for example, if the bit we have given is 16 bit, then the maximum value can be how much? 65 535. Okay, it depends upon the bit value, the maximum value changes actually. So in some cases, the prescaler may need to be adjusted to achieve the desired timer frequency of PWM output. So in some cases, the output can be adjusted to achieve a desired timer frequency. So the timer frequency, or the based on the pulse width modulation output, we have to change the prescaler. See, this is the prescaler. You can see this is the microchip. We are using STM32F10368T into LQFT of 48. So this is the microcontroller chip one we are using here for pulse width modulation. Okay, these are all the pins which are using here, and these are the mode selections what we have to change here and there. Okay, so see, for the channel 2 there is pulse width modulation, channel 2 is used. Okay. Again, next one is auto reload register. So what is auto reload register? Auto reload register, ARR, is a register used in timer modules to control the timer period. Okay, so this register is a register used in the timer modules to control the timer period. So this is the register which is used in the timer modules to control the timer register. So unless it is used here, nothing will be changed. Okay. So to configure the ARR in STM32, this is the name of the microcontroller we are using here. Need to first configure the timer's prescaler and the clock scores, and then set to the ARR value based on the desired time period. For the time period we are using for ARR, that is auto reload register, first we have to set to the timer of the prescaler and the clock source. Okay. Then this can be done using the timers control registers. Okay, this can be done using the timers control registers and programming interfaces such as the STM32Cube MX tool or the STM32 Hall library. Okay, for this only this can be used. According to this only this can be changed. So next, count up. What is the count up and countdown? Actually here for auto reload down register we need to count. We need to use the counter and timer. So for the counter it is used as count up and countdown. Okay. So the counter will count from 0 to the value stored in ARR and then generates an overflow interrupt and start all over again 0. So 0 from 0 onwards it is getting increased. So that is count up. Okay, to the startup value again from the 0. So what is countdown? Actually the opposite. The counter will count from the value stored in ARR. So in ARR something is stored, right? In auto reload register something is actually stored, right? So from this to the 0 value is again, that is called as countdown. Then what is actually count up from 0 to it is stored in the auto reload register, that is the count up, and the countdown that is from the stored value of ARR to 0. Okay. So here the auto register, see. The channel 2 is PWM generator, and here the parameters are given. From master to slave, modules are enabled and all others are disabled. Okay, so TIM timer 3 is used here. So this is the configuration for pinout and configuration. Okay. Next is duty cycle. As I already told you, the duty cycle is the amount of time a digital signal is in active state related to the period of the signal. Okay, so duty cycle is the amount of time a digital signal is in active state related to the period of the signal. It is the digital signal is in active state. It is always in active state related to the period of the signal. Duty cycle is usually given as percentage. Okay, I have already mentioned you what is the percentage. The percentage duty cycle is equal to T on by T into 100. So the T on is the pulse by ARR. Okay, so that is the percentage. So let me give you that the pulse is given as T on, which is divided by ARR, means the time which is used. Okay, so this is actually the duty cycle percentage T on by T into 100. Okay, T on by T into 100, that is given as pulse and ARR, that is auto reload register, where AR is the value of auto reload register, that sets the timer period. So that sets the timer period. So that is the card given here in this format. Okay, so for an example, let's see if the period P is equal to P is equal to 10 milliseconds. Okay, if T is equal to 10 milliseconds, the on time the T on time is 5 milliseconds. So what is the duty cycle will become? What it will become? Say the T on time 5 divided by the P not time period T 10 into 100. So what does it becomes? 0, 0 will get cancelled. So 5 into 10. So the duty cycle will become 50%, isn't it? So it will become 50%. So this is the answer for find out in the duty cycle in given format. Okay. So how does it gets measured? It always measured in the unit of frequency. Okay, frequency is always measured in the unit of frequency. It is used to calculate the transmission speed of electronic devices such as channel buses and computer internet. So channel speed of electronic devices such as channel buses and computers internal clock. Okay, so for as per the duty cycle, if the duty cycle is 0, it is always off. If it is 25%, it is 25%, it is always low power. Then if it is 50, then it is medium. Then if it is 75, then it is high power. Then if it becomes, the duty cycle will become 100, then it is always on. Okay, so no change in this duty cycle formation. Okay, don't never change it. That is, if it is 0, it is always off. If it is 20%, then it is low power. Then if it is 50%, then is medium power. Then if it is 75%, then is high power. And if it attains, the duty cycle attains 100%, then it is always on. Okay. See the measurement 1 hertz is equal to 1 cycle per second. Okay, it is given as 1 hertz for 1 cycle per second. 1 kilohertz is equal to 1000 cycles per second. Then again 1 megahertz. 1 megahertz is given as 1 million cycles per second. 1 gigahertz is given as 1 billion cycles per second. Okay. So 1 hertz, 1 kilohertz, 1 megahertz, 1 gigahertz has also been given. Again 1 millisecond is also 1000 of it second for 10 to 3. And 1 microsecond is 1 million of second 10 to 6. Then 1000 milliseconds is given as 1 second, and 1000 milliseconds, 1000 microseconds is given as 1 milliseconds. Okay, you understand how this comes? This is along with the measurements. Next, formulas. What are the formulas, important formulas we have to use in this PWM? For prescaler, that is one of the component for the prescaler, the system clock by frequency. This is the formula, the system clock by frequency. For the frequency, the system clock by prescaler. For the frequency, the system clock by the prescaler. Again, the frequency is 1 by time. Frequency is given as 1 by t. Again, the time is given as 1 by frequency. So this is the alternative formulas which will be coming for time and frequency. Again, the total time will give us start time into counter period. So the total time, how much is the total time consumed, is given as the starting time into the counter period. How many counters does it takes, the way it takes, that's the counter period. So the total time is equal to the start time into counter period. Again, ARR means auto reload register. So it is the on time plus off time, that is the ARR. So ARR means, it is very simple, you must keep in the mind, that is on time plus off time. Okay. Then duty cycle means on time by on time plus off time percentage. So it is also simply given as, how you can simply mention that this duty cycle, how can you mention this simply? Duty cycle means P on divided by T into 100. Okay, so this is the duty cycle easily mentioned. Okay, this percentage. Okay, you understand? So for generate a PWM for 1 second on and 1 second off, the system clock must be in which megahertz? 32 megahertz. Okay, the system clock should be always in 32 megahertz. Unless that, nothing is going to happen there. Okay. So this is one of the time by applying that formula pay scalar. If it is 330,000 in the frequency system clock by pay scalar, so 32,000 into 10 into 32,000, so it is 1000 hertz or 1 kilohertz. And again it is differentiated for time. For time the formula will become 1 by frequency, so 1 by 1000 is the frequency we obtain, so t becomes 0.01 into seconds or 1 milliseconds. Okay, this is the problem by applying the common formulas for the PWM. Again, this is the total time which is given, T into ARR. So what is the T actually here? 0.01 into AR has to be found out. So it is divided by like this. Then duty cycle 1 by 1 plus 1 is equal to 1 by 2. So for 0.5 into 100 we will get the 50%. So the duty cycle will become how much? 50% of the cycle. Okay. So the 50% of cycle means how many times, how like you will get the graph like this. Okay, this is for 50%. Okay, this is for 50%. So pulse duty cycle will be so 50% 2000 AL, so we will give the pulses 1000. Okay, these are the common calculations based upon the common formulas given on the PWM. So this is the result for 50% duty cycles. For 1 second it is on like this, then 1 second off, then 1 second on, then 1 second off. So this is the basic result for 50%. Okay, 50% duty cycle means the cycle graph will come under like this, under a square wave. Okay, for first on, first then off, then on, then off, like that only the results will be modified. Then what are the applications actually here? Okay, the PWM is widely used. The PWM is widely used in motor control applications, including DC and AC motor controls. Okay, for actually it is mainly used for DC and AC motor controls. Okay, the PWM is widely used in motor control applications, including the DC and AC motor controls. So by adjusting the duty cycle of the PWM signal, the speed and torque of the motor can be controlled efficiently. By adjusting the duty cycle of the PM. Duty cycle means T1 by T into 100, right? That is the duty cycle percentage. So by adjusting the duty cycle percentage, the speed and torque of the motor can be controlled efficiently in this PWM. Okay. Again, LED dimming. What is the application for LED dimming? PWM is common used in LED dimming application. LED dimming applications means it is also called as a breathing effect of the applications. Okay, so by varying the duty cycle of PWM, the brightness of the LED can be controlled efficiently. That is, it is actually assumed in the program by giving us 25, 0, 25, 50, 75, and 100. Okay, so by that, when you give for 0, it glows a little, then 25 it glows a little more. For 50 it goes to half the amount of its brightness. Again 75 more than that, then 100 it will give you full glowing. Again when you give the switch, press the switch, it will goes for from 100 to 75 it reduces a little bit, then to 50 it reduces half of its brightness, then it goes to 25 it reduces again little bit, then it goes to 0 and the switch is off, the light is LED is off. Okay, like that, this is called as the breathing effect, like that on section. So there is the dimming applications. Okay, so by varying the duty cycle of the PWM signals, the brightness of the LED can be controlled efficiently. The brightness can be controlled. For this, the brightness of the LED is controlled actually. Okay. So the next one is the power supplies. The PWM is used in power supplies to provide efficient power conversion and reduces heat dissipation. Okay, so this is the mainly used. PWM is used in power supplies to provide efficient power conversion and reduces the heat dissipation. So this is the main thing which has been used in this power pulse width modulation. And then is the By adjusting the duty cycle of the PWM signal, the average voltage of current delivered to the load can be controlled, providing efficient control over the output power supply. So it is nothing but by adjusting the duty cycle of pulse width modulation signals, the average voltage or current delivered to the load can be controlled, providing efficient control over the output power of the power supply. Okay, so output power of the power supply can be efficiently controlled using this pulse width modulation. Okay. So next application, it is used in audio amplifiers. Okay, audio amplifiers means pulse width modulation is actually used in audio amplifiers to provide efficient power conversions and reduces the heat dissipation. So it reduces the amount of heat dissipated from the system. Then again, it is by adjusting the duty cycle of the pulse width modulation signal, the average voltage or current delivered to the load can be controlled, providing efficient control over the output power of the audio amplifier. Okay, so it provides the load. So the load can be controlled, so providing efficient control over the output power of the audio amplifier. Okay, so some of the examples were Arduino, PIC, STM32. So here we are maximum using STM32, then ARM Cortex, then EPV32 and 8051. 8051 is the mostly commonly used microcontroller using the timers. Okay, so these are the examples used for this pulse width modulation. So what are the actual steps which can be used in this pulse width modulations? There may be configured with the timers and counters are, which configures the timer. It sets the pulse width modulations frequency. Then it selects the duty cycle. Again, it enables the pulse width modulation output. Then it is connected to the load. So according to the duty cycle of the PWM signals, the load can be varied, and so that the voltages or the current can be changed in the output of the power supply. Okay. So how do you write a program for embedded C on the based this? The PWM should identify it with the underscore of set duty cycle bracket of 75. So the duty cycle may be actually 75%. So that 75% amount of light will get, that is the relay will get close on the kit. Okay. So as I have told you in the early stages itself, why PWM? So that is the actual advantages of using this pulse width modulation. Okay, so that is the high efficiency, low power loss, precious control, and less heating, easy implementation, and longer battery life. So these are the advantages and the answers for why we are using the pulse width modulation in the embedded systems. Okay. So like with the advantages, there may be disadvantages too. So what are the disadvantages actually? Electromagnetic interfaces, here EMF interface EMI. So the high frequency switching noises can be also be a very big disadvantages for the system. Then requires filtering in some applications. So doing some applications, all the applications cannot be used directly into the output segment. So many of them needs filtering processes. Okay. So again, the more complex than simple voltage control. The voltage control is more complex here. It cannot be used as it is in the section. Okay, so it is more complex than the simple voltage control which are used here. So as per the real-time application, the LED dimmer light which is used for the brightness control, the DC fan that is used for speed control, the electric vehicle which is used for the motor drive, the drone which is used for the motor speed, the servo motor which is used for the position controlling, the robot are used for wheel controlling, the solar inverter is used for power conversion, that is A to D or D to C, then SMPS that is used for voltage regulations. Okay, so these are the real-time applications and how that applications are purposed or used in the field. Okay, so as per to be very shortly mentioning, PWM, that is pulse width modulation, controls the power by varying the pulse width. Okay, it varies only the pulse width, not the voltages. So duty cycle determines average output voltage. Only by using the duty cycle, the average output values voltage can be measured. Unless that, we cannot do anything upon that. And then frequency usually remains constant. Okay, so the frequency always will remain constant in this, and no change in the frequency, and the average output voltage will always remains gets changed. So while used in embedded systems for motor speed controls, while using embedded systems, while using the used in embedded systems for motor speed control. Motor speed control means maximum which one? Drone or electric vehicles or DC fans. These are the motor speed controlling vehicles. Then LED dimming, robotics, power electronics, and industrial automation. So mostly these are used in all these types of industries or automations for using the power control. Okay. So one more main point should be noted in this power pulse width modulation is frequency remains constant here and only pulse width changes. Okay, the frequency remains constant, that is the frequency here is always constant. So the frequency will be always constant and only pulse width changes, pulse width. So as per this, the frequency is really constant and the pulse width will get changed. Okay, there's no change in that, only the pulse width gets changed and the frequency will remain gets constant. Okay. So I hope you all understand the sections pulse width modulation. So please like the video. If you have any doubts, do ping in a comment. Okay. So hope we meet you all through your next video with a new topic. Thank you. Thank you all and all.